Welcome to Easy Alim Learning Simplified. My name is Ruth, and today we are going to be looking at the properties and traits across the periods. And for today, we are going to be looking at chlorides. Well, in the previous lesson, we looked at the oxides, and we were able to see especially the bonds on the oxides of period 3 elements and how that affects some of their properties. So today we are going to concentrate on the bonds of the chlorides and also how it affects some of the properties. And then we are going to tackle a few questions. So we are going to start the effect of the bonds across the period 3 chloride. So most of the elements in period 3 or the chlorides are usually form stable chlorides, and the type of bonds and structures and properties of chlorides of period 3, uh, they usually show a variation across the period. So we start with reactions with water. Basically, what you're doing, you're taking the chlorides of the elements along the period 3 elements, and then we are reacting them with different compounds. So how they react will basically be determined on the type of the bonds and the structure they exist in, just like we said with oxides. So reaction with water, when you talk about reactions with water, sodium chloride usually dissolves and magnesium chloride. But I want you to notice when these dissolve in water, they actually form neutral solution. This is a common misconception that we have. Magnesium chloride, sodium chloride, there's a tendency for someone to think that they dissolve in water to form basic solution, but their oxides are the one that behave so. So for their chlorides, they dissolve in water to form neutral solution. So take note of that. As for the other ones, aluminium chloride, silicon chloride, and phosphorus 3 chloride, phosphorus 5 chloride. These ones usually dissolve in water to form acidic solution. They are hydrolyzed. We're going to talk about what hydrolyzing is in a minute. So sodium and magnesium chlorides are usually ionic. So they have ionic bond between their atoms, and when they're added to water, there is of course that attraction to the polar water molecules. They dissociate into ions, and they usually form half-giant ionic structures. Anhydrous calcium aluminium chloride, on the other hand, is molecular. Normally, we would think that since aluminium is a metal, is reacting with chlorine, which is an unmetal, it forms ionic compound, but this is usually unique. Aluminium chloride is not ionic in nature, it is molecular in nature. It forms a dimer, and this is how the dimer looks like, and it usually has weak van der Waals forces between the molecule. So you have one molecule of aluminium chloride like this. This is a molecule, and then these molecules form a larger molecule, which is now the dimer. And the dimer is usually aluminium, aluminium chlorine 6. They have 6 chloride ions. And this is what happens. You can see the molecule and the molecule of aluminum chloride forming the dimer. You can be told to present this in dots and cross structures. Then how are you supposed to present this in dots and cross structures? So this is how you present it in dots and cross structures with the dimer. First of all, you draw the two aluminiums from those two molecules. So you put them in a two large circles, and then you start putting the chlorines. So what you'll do, you'll give the 3 chloride atoms or elements bonding to this aluminium a different color, and then you'll give also the chlorines bonding this aluminium a different color. So you start with the 2 chlorines first that are bonding this aluminium. And remember, one of the chlorine is also bonded to this aluminium. It's contributing some of its electron. So I'm going to draw a very interesting chlorine here. This chlorine is just showing that it's bordering between the two aluminium. And this is where the key thing comes in. So for this other aluminium, I'm going to use another color. So we also draw 2 chlorines and also have a chlorine that is bordering. So the key thing you notice in this structure is these two chlorines. These two chlorines are the ones that are going to help us to understand what is going on. So first we will distribute electrons amongst the chlorines that are not bordering the two aluminiums, and then we will go to the ones that are the center of the aluminiums. So let's do that. So aluminium, is atomic number 13. So the configuration is 2.8.3. Chlorine is atomic number 17. Configuration is 2.8.7. So when you look at this first chlorine, it requires one electron to be completely full. So we said it needs to lose that one electron, so it shares one of electrons. When it shares one electron, it remains with 6 electrons in the outermost shell. So those are the 6 that we put on the outermost shell, the remaining ones. Same thing happens with this chlorine. It's also atomic number 17. It requires one electron, so it shares also one electron, and the remaining 6 electrons are placed on the outermost shell. So let's go to these other chlorines. We also do the same with these chlorines, the two of them that are outside. So this chlorine also is atomic number 17, and also this one. So it also requires one electron, so it should share one electron. So we put the remaining 6 electrons around it. This chlorine also is atomic number 17. It shares one electron, and the remaining 6 are placed on the outer shell. So we have these two unique chlorines here. So let's discuss what happens. So I need also to put this aluminium here, 2.8.3. So we can start with the aluminium that is bordered with the black chlorines. So we'll give it the dots because we have used the X's or the crosses with the chlorine. So for aluminium, you're going to use dots. So when you consider this aluminium bordering the black chlorides, so let's discuss. It is 2.8.3. It has 3 electrons in the outermost shell. So if it has these 3 electrons in the outermost shell, let's discuss it together. If aluminium chooses to share these electrons with the 3 chlorines, how many electrons that aluminium require to be completely full? Aluminium requires 5 electrons to be completely full. So if it requires 5 electrons to be complete, but it only has 3 electrons, so what is going to happen to help it to be completely full? So 2 chlorines have already shared their 1 electron, so aluminium should do the same as well. So we are going to put a dot here, and a dot here, and we'll put a dot here. So this aluminium has shared its 3 electrons. If you are to count if it's completely full, it's not. Let's count. We have 1, 2, 3, 4, 5. So we require 3 more electrons. So these 3 more electrons are going to come this way. First of all, remember we have this chlorine here inside. This chlorine also is going to share 1 electron, but you're not going to put the remainder electron. Remember, it's 2.8.7. So it requires 1 electron. It needs to share that 1 electron. So now aluminium has 6 electrons, but it requires 2 more. So where are these 2 more going to come from? They are going to come from the chlorine bordering or bordered to the other aluminium. The chlorine, because it has delocalized electrons that are not used in bonding, it's going to share them freely. Remember, we called this a dative bond. So we know that this chlorine, let me use a different color. This chlorine here is going to share 1 electron with this aluminium, the original. We use cross. It's going to share 1 electron. So it's going to remain with 6 electrons. Among those 6 electrons, 2 of them are going to be given to this aluminium freely. Same applies to this chlorine down here, the black one. It has shared 1 electron with aluminium, but it is remaining with 6. Part of those 6 electrons is going to be shared with also this aluminium freely. So we can show that. So remember, now when you look at this chlorine, the black one, it has already shared 3 electrons. So it means it is remaining with 4. We put those 4. And the blue one, the same. So we put the 4 electrons. So you can see what has happened. However, we have not finished up with this aluminium. This aluminium also has 3 electrons, requires 5. It needs to share what it has first, the 3 electrons freely. But now it's going to receive also 2 free electrons freely from the chlorine that is bonded to the other aluminium. So you can see these chlorines are like helping each other. This aluminium helps this other aluminium with some electrons from their chloride. So this is where the dative bonding comes in. So that's the reason why when we are showing it, we are representing it, we put it like this. So this chlorine shares with this chlorine shares with this. This is what is happening. So this is what is happening at the center. This is what we refer to as the dative bond. So this is the dimer. This is the dot and cross in case you are told to present that in a diagram. So let's continue with the properties. So when aluminium chloride, the aluminium chloride that we have just drawn is placed in water, it hydrolyzes. So it hydrolyzes to form an acidic solution. So in so doing, it behaves like a covalent chloride rather than an ionic chloride. And this is the one that is unique. This is the one that is tested a lot because of its uniqueness. So if you put a blue litmus paper in a solution where aluminium chloride has been added, you'll notice it's going to change from blue to red. Unlike when you put the same blue litmus paper in a solution where sodium chloride and magnesium chloride has been added. Another unique property with aluminium chloride, remember it's behaving like a covalent structure, so it has weak van der Waals forces. That is actually the reason why it sublimes. Remember when we were talking about Form 1 work and we said that aluminium chloride is one of the compounds that sublimes. It sublimes because of the weak van der Waals forces between the molecule, so it requires very low energy to break those forces. So in the hydrolysis, it's usually an exothermic reaction which gives off hydrochloric acid, which is one of the products. So you can see the equation. This is just a general equation. So aluminium chloride reacts with water to form aluminium hydroxide and hydrochloric acid. Hydrochloric acid dissociates to hydrogen and chloride ions, which result to its acidic property. The same happens with silicon phosphorus later on, as you will see. So also silicon 4 chloride dissolves in water and hydrolyzes to produce hydrochloric acid. Hydrochloric acid then further dissolves in water and dissociates into hydrogen ions and chloride ions. So next we go to phosphorus 3 chloride and phosphorus 5 chloride. So phosphorus 3 chloride, phosphorus 5 chloride also dissolves in water. It hydrolyzes and to produce two acids, phosphorus 3 acid and phosphorus 5 acid, which dissociates to form the hydrogen ions, which brings in the acidic nature of the solution. So we have phosphorus 3 and phosphorus. So do not forget it forms two acids. And these acids are produced in the process, and also hydrochloric acid is produced in the process. So these are the properties. Note the structure and the bond type because it's going to affect a lot. So we only have giant ionic structure 2 and everything else is molecular with covalent bonds. And you can see how the low melting sublimation of aluminium chloride. And it's very clear. It sublimes, as I have said, because of the weak van der Waals forces between the molecules. So let's do a few questions. So the table below shows the properties of period 3 chloride, sodium chloride, magnesium chloride, aluminum chloride, silicon 4 chloride. Explain why aluminum chloride solid has a much lower boiling point than magnesium chloride. So we said that aluminum chloride is molecular with weak van der Waals forces between the molecule, while magnesium chloride is ionic structure with strong ionic bonds between a structure. So you require more energy with magnesium chloride than in aluminium chloride. Explain why anhydrous aluminium chloride is fairly soluble in organic solvents, while anhydrous magnesium chloride is insoluble. So when you talk about organic solvent, you're talking about non-polar solvents. And we know that non-polar solvents usually dissolve better in other non-polar solvents. Organic solvents are usually molecular in nature, they are non-polar. So aluminium chloride is also non-polar because it's molecular. But when you look at magnesium chloride, it's ionic in nature. It dissolves in water to dissociate into iron, so it is polar. That is the reason why the anhydrous aluminum chloride dissolves in organic solvent while magnesium chloride does not. Sodium chloride dissolves in water to form a neutral solution, but aluminum chloride dissolves to form an acidic solution. Explain this observation. So sodium chloride dissolves because sodium chloride is ionic in nature, dissolves in water to form a neutral solution, but aluminum chloride hydrolyzes to form hydrogen chloride, which makes the solution to be acidic. So I've just done a summary on the questions, but I've given you the key things in the questions so you can write down the statement yourself. So that brings us to the end of the period 3 elements. We have tackled everything in period 3. So our next lesson, we are going to tackle a new topic, but I hope you have been able to see how the chlorides are. This is a very commonly tested questions, especially period 3. Make sure you go through the videos again so that you can be able to understand the parts you've not. So see you in the next video.